Okay, we're going to take some time to go through a few concepts out of Chapter 5. Most of these are concepts that you've probably heard of before. I just want to make sure that you understand what what is being referred to in the book. So the first part of this, we're going to talk about different types of data. And when we talk about data, really what we are getting down to is terms that we will identify as variables. And we talked the other day about independent and dependent variables, how one thing affects the other. In quantitative research, whether we're talking about inferential statistics where you're trying to say something may or may not be true of a population based on your sample, or you're just using descriptive statistics, descriptive research where everything you have access to everything that you're talking about, everything has to have some kind of variable. So a lot of the terms that we're familiar with in schools and educational research is grade and age, gender, ethnicity, geographic location, type of schools, meaning elementary, middle, high school, test scores, and those are a different kind of variable. Teaching method, somebody might use group methods, single instruction, small groups, group learning from Kagan. Those can be categorized. Student categories, they can range from high performing, low performing, low SES, non-low SES. That can be divided into free lunch, reduced lunch. There's just about every way that you can think of to categorize something. All those are variables. What happens is they're not all the same kind of variables. So before we do anything else with our data, we have to put it into usable form. So we're going to go through a few examples of these. Ordinal data means that the data is placed into ranks or in relation to one another. For example, class ranks, letter grades, Likert scales. All those are ordinal data. And the challenge with that, I want to remind you about one of the videos that I did about being able to choose the right kind of test depending on the type of data, is you can't take averages of ordinal data. You can't take the person in the first position in your class, second, third, fifth, seventh, and eighth, and take an average of that. That's just not what that means. You can't do that with letter grades. You can't do that with Likert scales. And that goes back to the job involvement scale, where we had strongly agree, disagree, converted to 1, 2, 3, 4, 5. Simply changing that to numbers does not mean that it is all now as a raw score, whether it's interval or ratio. It is still ordinal data. You still cannot take the averages. That's an important difference because it sends you down a different path of statistical tests. Raw scores, there's two types. There's interval or ratio. And simply stated, these are just numbers, like years of experience is a dollar earned. The real difference between an interval and a ratio has to do with the zero. So for example, with interval data, there's a specific order with equal differences. The easiest way to think about that is temperature. Temperature, the degrees, goes by a single digit. But the zero doesn't mean the lack of temperature. It's just a point on a scale with equal differences. The difference between -1 and 0 is the same as 0 and +1. Ratio data is a specific order with equal differences and a real zero. The easiest way to remember that is something like money. It is possible to have $0, and that means there is nothing. The zero is a true place value. So those two types of data, even though you're not really supposed to treat interval data with mathematical equations, we're going to in statistics. That is a different type of statistical test as well. Nominal data simply means if I need to apply a numerical piece of data to a category. So for example, which group that you're in. level, socioeconomic status, your gender, your ethnicity, your political affiliation. If we had 5 different types of ethnicity in a school district, and we had 20 in one, 22 in another, 100 in the third one, you can't take those together and average them and get a 2.2 on ethnicity. That doesn't mean anything. Dichotomous tests are those where there's simply a yes or no issue. Either the attribute is present or it is not. So the reason that this is important is because the type of test that we use really depends upon the type of data. So there is a column here, and I alluded to this before, called, these are the types of measurements. So everything in this column is going to be interval or ratio data. And I want to point out what it says about Gaussian. That means a normal distribution. So if I want to compare one group to a hypothetical value, that's a one sample t-test. If I want to compare 2 groups, that's an unpaired t-test. If I want to, I'm sorry, 2 unpaired groups. If I want to, that means like pre-post. If I want to compare 2 independent groups, that's a paired t-test. We can do those same kinds of things if we have ranked data, scores, or measurements from non-Gaussian populations. That means non-normal distributions. So if I want to compare pre and post on a survey, I actually use something called a Mann-Whitney test. If I want to compare 2 groups, 2 independent groups, I use something called a Wilcoxon, and we'll go over what all these are. It's really important to keep these in mind because, as I told you before on one of the other videos, picking the wrong test can give you a different answer, and it increases the likelihood that you're going to say something that's true, or say something that's true that's not, which is a type 1 error. It's extremely critical not to do that. So all of that is based upon this type of data. If we use the wrong test or didn't pay attention to the data, you get a different answer. So I'm going to refer back to these 2 videos. I want you to go back and look at these again. There's one about the job involvement scale, and then there's one about why we do statistical analysis, why we use inferential statistics. So measures of central tendency. We have 3 main types, and everybody has a favorite, but they are not all created equal. They all have a use, but they all have a risk. The most common one that we go to is the mean, the arithmetic mean, where you add them all up and divide by the number that you have. There's the median, which is the score in the middle, and there is a mode. That's the score that occurs most often. Even though these are all available, the one that is the least stable, the one that is the most at risk to not being accurate, to not being the best measure of central tendency, is the mean. Here's why. So here's a list of district administrator salaries. We can guess who that probably is. And here's the other district administrator salaries. So bear that in mind, and let's look at this. If someone complained about the administrator salaries because the average was $94,962, that's probably going to offend 10 of them because it's not the best representation of what's occurring. So look at this number. There's not very many people that are making that, and actually most of them are making well below that. That's why these 2 numbers, and actually this one in particular, is causing a problem. It's not the best measure of central tendency. The median and the mode better represent all the administrators, where the median is 87,245 and the mode is 87,678. This depends on a normal distribution, but sometimes things are not normal. And what I mean by a normal distribution, and I know that you've seen this before, is this: how numbers get distributed along a normal curve. Just because we're using a mean, that does not necessarily indicate that they are distributed in a normal way. If we have a large enough data set, we can assume that the scores distribute evenly from small to large. And the easiest way to understand this is an IQ. So we all know, or should know, that the average score on the IQ exam is 100. And incidentally, that's not technically true anymore. It actually went down. The average IQ score is now like a 99.6 or something like that. So if you thought the world was getting dumber, you're correct. Just as a sidebar, here's why. They have, based upon a study that came out of England several years ago, is estimated that really, really smart people are choosing not to have very many children. They'll have none or maybe one. But the people that are not quite as intelligent, perhaps down here on this scale, are having lots and lots of kids. And it is actually pulling the average down. So that's not necessarily true, but we're going to go with that for now. So let's make sure we understand how this works. The mean score of 100 is right here. So of all the people that are scored in the world on an IQ test, 50% of them will be above the mean, 50% of them will be below the mean. The IQ scores are divided by standard deviations. The standard deviation for an IQ is 15 points. So one standard deviation above the mean right here is 115. One standard deviation below the mean right here is 85. This area tells us the percentage of people that are between 85 and 115. So this would tell us that 68.26% of the people have an IQ score somewhere between 85 and 115. When you move to the next band, the distance from here to here is 15 points. So 2 standard deviations above the mean is a score of 130 on IQ. And that would also tell us that only 2.27% of the people in the world have an IQ score higher than 130. Right here is 145. So there's only 0.13% of the population that has an IQ score higher than 145. So all scores that are normally distributed will have standard deviations. And if they're truly normally distributed, they'll look like this. The challenge for us is that doesn't actually happen very often. It is a very rare thing to see that, and actually what we normally end up with is a non-normal curve. So I'm going to pause here because these are 15-minute videos and start another one in just a second.